Is that great? It's a great pleasure to introduce Danny Terno. I know Danny Terno since we were both postdocs, and he's the person that I know the oldest, sorry to use this word, merging quantum information with things like in relativity and so on. So it's a super pleasure to introduce him, and he's going to be talking about how to use information.
Thank you, Yvette. And well, thanks to Gata and Jonathan for organizing this symposium. It's always nice to be in London, especially when it's warm, outside the tube, of course. And it's great to see so many people, well, and tell some of my favorite stories. I have to make an admission. Yvette partially disclosed it. I come from quantum information. I am not trained as quantum fundamentalist. I occasionally fell into fundamentalism, even without actually trying. So many of the questions that I'm going to ask are the questions of a fundamentalist that tries to convert them into math and then stick to the bitter end no matter what without changing the definitions. So that's sort of the heads up. Now, let's start from the story. I think everybody knows the story. On the left, we have a Penrose diagram with Hawking's sketch of the Penrose diagram of collapsing black hole that subsequently evaporates with all kinds of lines and infinities. And probably the best summary of the reason for my talk was given by Bob Walden, Living Reviews of Relativity, almost horribly quarter century ago, that when a black hole evaporates via the Hawking process within a finite time, and if the correlations between the inside and outside of the black hole are not restored during the process, then by the time that the black hole has evaporated, an initial pure state will have evolved to a mixed state. That is, information will have been lost. Since then, we also talk probably more about entanglement than just correlations. And that's the gist of the problem. We have to make it precise so we can better ways of arguing. Now, as a curiosity which shocked me when I was a grad student was that Hawking proposed to describe this process evolution of a pure state into a mixed state by means of a superscattering operator. And in his 1976 paper, he was rather apologetic about introducing it, which is fine. The point is that the same 1976, that's where people in what became quantum information community were playing with completely positive map and Lindblad equations. And my first impression when I read about this thing in the textbook of Frolov and Novikov was, what the hell, what the problem is just a CP evolution. But that's, as again, Jacob Bekenstein explained me once, the communities were just living parallel lives without even suspecting of existence of each other. Now, how we deal with this problem? Like a standard way of dealing with a crisis, there are several stages. You can exercise it, you can deny it, you can accept it, you can embrace it, and probably there are a few more ways of dealing with it. Now, what I'd like to talk, as I warned you, I'm fundamentalist, so I will look at it as how to formulate the paradox. We'll talk actually a little bit about structure, how you formulate paradox in quantum mechanics. What do you need? Now, we'll look at information loss from the same perspective. We'll look at the ingredients which are necessary not to resolve the paradox. I do have an opinion, and if you poke me sufficiently strongly, I will venture this opinion, but I'm not going to say it voluntarily. My approach today is to look what you need to consistently and honestly formulate it as a paradox. We'll look then what are the black holes and which features they should have and what follows from this. We implement it and look at the consequences in spherical symmetry, simply because it's easier. And we'll talk about, if we have time, we'll talk about potential observational signatures. So let's look at the paradox. So we have here Katz-Schrödinger and ER equals EPR and introduction to Kabbalah. Those come together very nicely. But looking at the paradox, what do we actually have? Think about Bell inequalities, think about quotient-Speckers, think about wave-particle duality. You have classical structure. You have classical ideas, assumptions, results, beliefs, or things that you want to enforce. Then you have quantum features or laws of quantum mechanics. You have some laws that you have to live with, and then you trying to mix them in such a way that all of your beliefs are consistent. So you want to reconcile the 1 and 2, and you want it to be logically internally consistent and correspond to predictions, to experimental observations. So anything which we know strictly of the paradoxes falls into this category. So EPR, quotient-Specker. If we talk about black holes, yes, info loss also is built from those bits. Firewall, well, just 5 axiom contradiction, also structured the same way. So for black holes, we need 2 things. Now, why the numbers 2 and 4, you will see in a moment. But we need the event horizon, and that's the classical concept. And we need, say, Hawking radiation. That's what comes from quantum mechanics. Now, a role of event horizon is really interesting and evolving. Now, although these are quotes from Hawking, which were collected in the paper of Hayward in 2005. So starting from the essential property to something that maybe doesn't exist. So one way of the radical solution, there is no event horizon, no paradox. Tons of works are written about it. Let's say in 2017, two papers were published back to back in Reports on Progress in Physics, with a paper by Don Maralf saying, no, there is no paradox, giving several ways to explain it. And the paper of Andrew and Wald, which probably can be entitled like, so what? And sort of learn to live with it, it doesn't hurt. More modern views, again, from different sides of the divide and different solutions.
That so what is to the general paradox or to that answer? No.
No. It's to the paradox. It's like, okay, there is information loss, so what? It might even cause it might even cause a non-conservation of energy, but to such extent that we're not going to see it. So what? Okay. So now let's see what we really need to have the paradox. And I mean paradox, not just a complicated computational problem, which is hard and is not going to go away even if we exercise the paradox. First of all, we need finite time of formation and evaporation, according to distant observer. So it's in and out setting, but in practice, the thing becomes physically relevant only if it's accessible to mortal, even maybe very, very well-funded observers. So finite time of formation, finite time of evaporation. We need event horizon. Event horizon is an essential part, the essential part of the paradox. We are tracing out, and we are tracing out not because we don't have enough budget to do experiments over there, like our usual tracing out, at least pretend that that's our usual tracing out in physics, statistical physics, but some tracing out because of a fundamental reason. And that means that's why we need the event horizon. We want something which is observer independent. Then we assume, to formulate, remember, we formulate it within the semi-classical framework. So we need this semi-classical framework to be valid. If we want it to be valid, that's why we must take the say firewall gang, as they said, no drama at the horizon. We want, in principle, it's taking weak cosmological censorship, that there are no singularities outside or on the horizon. We don't care about deep inside, but within in the vicinity, standard semi-classical physics should apply, at least most of the time. Yes, and of course we need nearly thermal Hawking-like radiation. And that's the purpose of it. Again, what's the purpose of Hawking radiation in life? I don't know, but the purpose of Hawking radiation in the information loss problem is to generate high entropy state. And then we have a contradiction between low entropy initially, high entropy at the end, and that's what we interpret as entropy non-conservation. Now, what I'm using it as a motivation for the framework I'm going to present, and it's exactly what we take from these four assumptions. So if I'm going back, we have really key assumptions 2 and 4 for the paradox, and we have also assumptions 1 and 2. Now, I'm going to ignore 2 and 4 at the moment, because again, I'm a peaceful person. I'm not looking for controversies. I'm going to look at what happens and what does it take to have finite time of formation and to have no drama at the horizon, and what is the price. So let's turn existence of black holes into a mathematical question. So that the first black hole, more than 240 years ago, Reverend John Mitchell, his famous letter. Now, by the way, those who haven't read the paper, you know that this is not the abstract. That's the title. And then on item 16, he got to the estimates, and the estimates were quite right. Now, another interesting thing about black holes, I had my dark suspicions. They were fully vindicated by a reading letter of Eric Curiel from Nature Astronomy in 2019. He basically interviewed people who work on astrophysics, mathematical relativity, quantum field theory and curved spacetime, strings, quantum gravity. All of them have black holes, and asked them, so what is the black hole? And then he tried to find sort of the lowest common denominator. And it seems like the lowest common denominator was that black holes are the massive objects that they happen to work on. So we have to be very careful, and then we have to remember some wisdom from Kunze about importance of the definitions. So in our game, I'm going to adopt particularly terminology of Valery Frolov, and to distinguish between two types of black holes when I'm saying black holes, and I will add an adjective to them. So we're very clear. So on the one hand, we have mathematical black holes. That's what we study when we study general relativity in textbook. So basically interior or outside of the boundary of everything that doesn't get to the future null infinity when we're talking about asymptotically flat spacetime. Let's stick to asymptotically flat spacetime for a moment. Eternal, we need to know the entire spacetime history. So it's really like God's outside time. In practice, most calculations of numerical relativity, you don't calculate the event horizon, you calculate the apparent horizon and then assume certain things and draw the lines. On the other hand, there are what he called physical black holes, and I apologize, I used to write P, but too many people were unhappy because it's like primordial, so physical will be with phi, and those are just trapped space-time regions. Roughly saying, bounded by the apparent horizon. There are varieties of very careful definitions that I'm deliberately glossing over now. In spherical symmetry, where we work, they're more or less the same. So trapped, marginal, untrapped. We'll look at the expansions of two families of null geodesics, orthogonal to sphere. Both of them expansions are negative. We're in the trapped region. Outside, what we conventionally call ingoing has negative expansion, what we conventionally call outgoing has positive expansion. So that's a physical black hole, and with that, I propose to play. So, of course, we know that in standard stories, when we have classical matter, apparent horizon is behind the event horizon. We get very nice singularity theorems, which are based in particular, well, on at least classically, on the satisfaction of the null energy condition. We also know that Hawking radiation changes it. apparent horizon and parties outside the event horizon, and all kinds of interesting properties happen. Now, with these definitions, we can come and identify animals in the zoo. So what, now I apologize, this is epsilon. Apparently my character set is not very compatible. So adapting and modifying slightly pictures from article of Cardozo in Pani, we analyze various ultra-compact objects. Now we really want to compare this ultra-compact object, again, let's say spherical, to Schwarzschild black hole of the same mass. So we introduce compactness epsilon. By how much, which it tells us by how much size of this object is bigger than the Schwarzschild radius of the entity of the same mass. Now we know that astrophysical black holes have light rings. That means models that purport to describe them should be sufficiently compact, and they have to have compactness smaller than 1/2. Then there is a whole zoo with very important physical characteristics that distinguish between them, and what I have here is just a very crude picture of it. And again, I'm not going to enter into this. What I'm going to mention that if compactness is smaller than 1/8, those things called exotic compact objects. They're called exotic because they have to violate at least one of the assumptions of the Bohdal theorem, and all those assumptions seem to be pretty reasonable. How compact spherically symmetric static object can be if it's not a black hole. So something gives in, so that is an exotic object. Now, because we might run out of time, I'm going to tell you a secret now and not repeat it in the summary. So if we stick to physical black holes and assumptions of 1 and 2, then so it means finite time of formation and absence of singularities on the horizon, those entities are more exotic than exotic compact objects because they have to violate all 4 assumptions of the Bohdal theorem. But that's for the future. Now, let's see what can we have from the logical perspective. Remember, I'm a fundamentalist. So from the point of view of a distant observer, the collapse can be just never-ending, asymptotically reaching Schwarzschild or Kerr solution thing. At least many models of classical collapse, those are the asymptotic states. So epsilon goes to 0 at time of a distant observer going to infinity. People, for a variety of reasons, are unhappy with these solutions, and they generated a whole lot of exotic compact objects where we get a transient or an asymptotic object where compactness reaches some minimum at finite time or at infinite time. That's class 2. Of course, we can also have wormholes as models of black holes, and they can be as compact as a black hole. What I'm curious is, remember, we want to formulate honestly information loss problem. So we want finite time of formation. So let's consider what happens if we have trapped region in finite time of a distant observer. That's the assumption 1 in the list of criteria for formulation of the information loss problem. Good. So let's define rules of the game. So I want the classical space-time structure because we work in semi-classical physics, even if honestly it's the only thing that I know how to do more or less, so that's why it's semi-classical. We use classical concept. We assume that metric is modified by quantum effects at the level of semi-classical Einstein or Müller-Rosenberg equation. Right-hand side will stick there renormalized energy momentum tensor. So there might be higher order curvature terms coming from regularization. It also might not be GR. It might be F of R theory or anything else, which is the metric theory. This is the only thing that I care. Left-hand side, we stick Einstein tensor. Right-hand side, everything else. And we're primarily going to focus on the Einstein tensor. Now, we do not assume global structure. We do not assume existence of event horizon. We don't assume existence of singularity. We don't care which quantum state it is. So we're trying to do more thermodynamics and statistical physics in this case. And obviously no opinion on presence or absence of Hawking radiation. Let's see just what happens from requiring that the light trapping region forms at finite time of a distant absorber. We take the minimal form of regularity, and that means curvature scalars that are contraction of Riemann tensor, only Riemann tensor, not derivatives, are finite on the boundary of the trapped region. And the theory is consistent. That means quantum energy inequalities are not obviously violated. So energy density and whatever can be negative. Null energy condition may be violated, but there are quantum bounds on this violation, and those bounds should be satisfied. So that's all we ask. And because, again, let me drill in a little bit again about motivation. So one hand, why we do this, if we play spherical symmetry, particularly easy in a symptotically flat space-time. If we want to talk about event horizon at finite time, it's quite easy to show that then apparent horizon should form at finite time. If we want to talk about regular black holes, that means objects with trapped region without singularity that appear and disappear. Or we want to talk about black to white hole bonds. We need finite time of formation. And finally, actually, question. Are you more Star Trek or Star Wars people? I know it's very political. I know that it's politically incorrect question. It's really can cause trouble. If you want traversable wormhole, wormholes road in most conventional definition, unless you want to stick in some singular matter distributions, is marginally outer trapped surface subject to the flare out condition. And that means we want marginally outer trapped surface in finite time. But that's a different story. It's more about why my kids stopped talking to me for 2 days after I published one paper. But now let's look at the implications. So without going to formulas first, let's do the project process. I'm going to use a Schwarzschild coordinate in spherical symmetry. That both lets me to figure out what is the finite time of a distant absorber, and those coordinates are bad coordinates. In those bad coordinates, things diverge. And quantum field theory taught us that it's good when things diverge, because when you cancel the divergences, you learn about the structure. They cannot diverge in a random way. They have to do it in a coherent way. So you build from divergent quantities something finite. And from this, we'll be able to understand something about energy momentum tensor, and from there back and forth about the solutions. And once we've done it, then we will move to null coordinates, and they will help us to classify what are the objects that we obtain. As an advertising for those physical black holes, then not surprising, we'll get finite infall time. We will get that solutions come in pairs, shrinking black hole and growing white hole. If you play with collapse of massive thin shell, it might take a finite time according to distant absorber, but there are potential issues with sufficient violation of the null energy condition. What we do know that outer apparent horizon, if it exists, it's time-like. Inner horizon, time-like or null, but looks like it's always time-like. In the vicinity of the outer apparent horizon, null energy condition is violated. In the vicinity of the inner horizon, if it exists, it's satisfied. And then there is a curious thing which happens to surface gravity. Surface gravity, we can say it's in certain sense a measure of an affinity. It's measure how much force you have to apply to hold the thing just outside the event horizon. And in steady state, it's also proportional to Hawking temperature. Generalizations to dynamical cases exist, and there are many, and usually they are slightly different, but pretty close. What happens that this finite formation time plays havoc with most of them, and Kodama surface gravity that I'm going to introduce later if we have time is good and moves transfers flawlessly. But with this transfer, it causes some additional interesting problems. Okay, and now to the details. So this is what we use. This is what we assume first of all. Spherical symmetry, only two metric functions. We can take the outgoing null, parameterize outgoing family of null geodesics. We can calculate the expansion, and we know that the boundary of the trapping or anti-trapping region is where the function f, which is 1 minus 2m over r, we'll see it in a bit, is 0. So we use bad coordinates, we use the self-renormalization, and the last bit of technicalities is to pick up, Einstein equations. I mean, it's the most beautiful thing in physics, but Einstein equations are ugly if you have to solve them. That's really painful. So one of the things is to try to find the least painful way of using your variables. And this least painful way is twofold. We'll look at two curvature scalars. If those are finite, then we can show that everything else is finite in spherical symmetry. So we take trace and the square, and again, of the entire right-hand side. So more honestly is G and curly G. It's the geometry. We use different effective components. So covariant, mixed and contravariant, sticking into some of them e to the power minus h or 2h. Because this way I can avoid something that I don't know, and I can express things relatively nicely. So if I do this, I find that two curvature scalars that I have to check, and I want them to be finite, this plus regular terms. It's possible to prove that the rest will be at least less singular than those. And that means I need all those effective components to go to 0 together, or go to a finite limit together, or go to diverge together. More careful analysis shows that only two cases are legit and don't lead to trouble. Either they go to constant limit, or they scale as the first power of the function f as we approach the apparent horizon. Now, that's why my assumption 3 that I wrote, consistency, becomes important. That's what my students recently pointed out, that I was too hasty and I dismissed negative powers of k using sort of hand-wavy arguments, which are not good enough. And to really exercise them, we need to appeal to quantum energy inequalities. If if those components diverge, then we can construct finite curvature scalars, but we get infinite negative smeared energy density. So that's why we stick only to the classes 0 and 1. In class 0, two of the functions must be negative, because if I take the opposite sign, I get complex value solutions. The flux may be negative or positive. If we expand the Misner-Sharp mass as Schwarzschild radius plus the rest, we can get first terms in this expansion. So the two classes of the metrics will look like that, which in Schwarzschild coordinates, they look very unlike Schwarzschild black holes. In retarded or advanced coordinates, they look much more familiar. Because we have more Einstein equations than metric functions, we have relations. Now, ignore the formulas for telling a story. We know that we have two classes, k equals 0, k equals 1. There are also static k equals 1, but no dynamic k, no static k equals 0, but there are static k equals 1 solutions. All idea metrics are k equals 0. Reisner-Nordstrom, static regular black holes, and everything else static that I checked so far, they all belong to k equals 1. Dynamical regular black hole models, they all belong to k equals 0 class. So you just take the model, do tests, and they all fall into those classes. To understand what I've got it's convenient to use advanced and retarded coordinates. So we can do coordinate transformation, and it's possible to obtain some explicit form. Here I wrote how energy momentum tensor looks like and how Einstein equations look like in using advanced coordinates. Again, never mind this. Look at the message. If we have Schwarzschild radius shrinking, what we get is that a regular coordinate system involves advanced coordinate, and then simply to verify that we have shrinking black hole. If we have growing Schwarzschild radius, we have as a regular system, we have retarded coordinate, and we have white hole. So we have shrinking black hole, growing white hole, both for k equals 0 and k equal 1. Okay, apparent horizon, antitropic horizon, time-like membrane. It's possible to calculate the finite in the infall time is finite, the redshift is finite, and all it depends on on the evaporation rate. We can get energy density, we can write things in, let's say, advanced coordinates, and then they look suspiciously like what Bardeen wrote in 1981. Again, never mind the exact formulas. Another bit of story, energy conditions. So with the energy momentum tensor that we've got, we find that null energy condition is violated. So out of 4 idea solutions, shrinking, growing, retarded coordinates, advanced coordinates, 2 are excluded. They are happening beyond the end of time. Those that don't violate the null energy condition. They're very interesting, but for us, for mortal observers, going to happen. Now, an interesting feature is that 3 components, remember, go to the same limit. That's what we've got in our k equals 0 solution. Now, if you look, for example, at ab initio calculations, full 4-dimensional calculations of a renormalized energy momentum tensor for under vacuum on the background of Schwarzschild, done by Levy and Ori, you will see that these 3 components go to this limit. So that was one first indication that probably what we are doing is not totally nonsense. Okay, another story. How the black hole forms. Well, again, I don't know. What I can do, I can try to describe it and see what I can get just out of this description. So what I'm doing, I'm still expanding, sticking to advanced coordinate, I'm expanding the Misner-Sharp mass as a point at which we have a minimum of the difference C minus R. That will become the Schwarzschild radius later. Correction and the expansion terms. And by doing very simple calculus, we get that formation of the first marginally trapped surface requires the coefficient W1 equals 1, which corresponds to the solutions of the class K equal 1, subsequently transforming into class K equals 0. So what it, again, with a little bit of other work, what we see that if we do have a regular black hole, then we don't have blob structures. We have time-like surface at the moment of formation. So we get what looks on the diagram as a point, which is a 2-sphere. We can define event of formation, unlike the standard amoeba-like models. A byproduct, black holes, spherical symmetry, finite time of formation cannot grow. So the growth stages of the popular model are self-contradictory. If it's a transient regular black hole, so there is what they call disappearance or evaporation, the same story happens in the reverse there, provided that you believe in semi-classical gravity. It's also possible to accommodate the bonds. Of course, black holes cannot grow, white holes cannot shrink, but nobody, at least in principle, prevents the inner horizon to grow faster than the outer horizon for white hole. I don't believe in it, but geometrically we can accommodate. And there are 1+1 calculations in which people get sequences of black and white hole solutions, and they fit, apparently they fit into the spectrum. Cool. So now let's get something again towards the formulation of the paradox, or problems with formulation of the paradox. So yeah, we want finite time of formation, we want regularity. This is what we get. Those are the conditions to have those solutions. Great. Violation of the logic condition, fine. Now, about Hawking temperature, I cannot really say honestly, because I haven't done real field theoretical calculations of this background. But you know, to throw the doubts, as a good lawyer should, my colleagues looked at the surface gravity. So surface gravity can be measured, again, can be defined, again, standard general relativity for static black holes is an affinity of null geodesics on the horizon, and also how null geodesics sort of peel off if they're near the horizon. One physical interpretation is that it's a force per unit mass as measured at infinity to keep the observer stationary just outside the horizon. And in standard static spacetime, so say Schwarzschild spacetime, all those three definitions are equivalent. And surface gravity for Schwarzschild in Planck units is 1/4 mass, or in our notation 1/2c. And stick proportionality, well, dimensional coefficients, and you get the Hawking temperature. So that's very, very important quantity. And naturally, people looked at the generalizations into dynamical space-time. It's important because, first of all, it plays the key role in black hole thermodynamics. It's a bit self-contradictory because on one hand, we need, well, null energy condition is true, then the surface gravity is constant on the horizon, and that's equivalent of the first law of thermodynamics, Zero's law of thermodynamics. Surface gravity, generalized for axial symmetry, works also in the first law, and that's one hint that it works or looks a bit like a temperature. Now, it is also proportional to the Hawking temperature. In this case, null energy condition is false. So surface gravity is a really, really important entity. And there are two, well, there are more, but roughly there are two classes of surface gravity. One using Kadama vector, which is definable in any spherically symmetric space-time, dynamical or not, or using the peeling property, which again, in spherical symmetry has a relatively easy definition, and there are varieties. And what was shown that under quite general conditions, you get slightly different expressions, whether you go this way, or which particular of the ways of peeling gravity you go. But for macroscopic black holes, those differences are small. The problem for those guys, it breaks down if you assume finite time of formation. You just get divergent limits, or you try to regularize them, again, depending on the specifics of the definition. So you can get 0 identically, you can get infinity identically, and probably you can get whatever you want. On the other hand, Kadama version of surface gravity has pretty straightforward formula. We can write it as an expansion, and it transforms beautifully, assumes all the nice limits, and has only one problem. Remember, we said that black holes apparently form finite time as k equal 1 solution. K equal 1 solution, W1 equals 1. Plugging it all in here, we get that Kadama surface gravity at the formation is 0. Now, what? Okay. This one don't want. another one. We'll leave not in yeah. So we'll, and honestly, I don't know what to do with it. It's a doubt. So really honest calculation of radiation through the early formation stage should tell us what is the relationship with Hawking temperature, if any. But one thing that worries me and makes my life interesting is that, okay, to form the trapped region, we need to violate the null energy condition. So we need a mechanism to generate exotic matter. If we have collapse of normal matter, somehow we need to prevail over the normal matter by creating enough exotic matter. And the only process that I know which exists now and not unknown physics is Hawking radiation. But Hawking radiation is related to surface gravity. And we have that surface gravity exactly at the formation moment is zero. So it sort of joins a line of arguments that say that quantum effects are, well, either not strong enough or weak enough, depends on your point of view, that prevents formation of the horizon. Again, I don't know. Here I just sowing doubts. What else can we do? And that actually leads to maybe only one observable prediction that we have so far. And again, it's not prediction, it's a prediction in the style of quantum fundamentalists. Believe not in flat spacetime. Sorry, not asymptotically flat spacetime. Asymptotically de Sitter is probably much more appropriate. What happens is that with our choice of variables, if we separate our effective components into cosmological constant and everything else, very little changes. Nothing changes in the requirements of regularity. Again, it's a local requirement. Einstein equations look almost the same. There is only one of them which changes. And that means our formal solutions are fine. For example, the idea de Sitter obviously fits this classification scheme. And again, is K equals 0 solution. And we can draw a Penrose diagram. That's our static patch. Or let's say this is for a regular black hole. And those are different interesting surfaces that I'm not going to bother with. Good. So in the last 5 minutes, I'm going to talk a little bit about connection to observations. And maybe, and maybe let's start with cosmological ones. So about 2 years ago, there was a minor scandal in astrophysics and cosmology community. Results by Crocker and collaborators, so the result of several years of theoretical investigations and then analysis of observations. They were asking the question how black hole size, astrophysical black hole size, mass is related to global expansion of the universe. You can parameterize, you can at least phenomenologically, you can parameterize it that let's say black, ignoring obviously Hawking radiation for cosmological size black holes, that you can parameterize it as mass now, where A is the scale factor of the Friedmann-Robertson working universe now, related to the mass at some initial time, as a ratio of the scale factors to some power. Obviously, if we say that the power is 0, then there is no relation whatsoever. And there is intuitively simple, and there is no coupling between black holes and expansion of the universe. Now, they claimed, and I'm totally unqualified to pass any opinion on validity of the result. They claimed that observations actually best fit is that the power is 3. And then if the power is 3, you can derive the equation of state for astrophysical black holes, which corresponds to dark energy, and it's very cool and neat. Then there were different arguments why the data is wrong, why it's inconsistent with some other observations. And again, I'm not in any position to comment on that. What we can do in a good quantum fundamentalist tradition, we can take this as an assumption. Let's assume that there is cosmology. Well, let's see what does it mean if this is so. Is it compatible with black holes having horizons? So the black holes in question being really physical black holes. Now, what we can do, we can look at distant observers, which are asymptotically static, de Sitter region, far from cosmological horizon. Then there is not much difference between moving time and static time. Using the definitions and changes of variables, what we can see is that the dr over dA will be, first of all, if it's non-zero, it will be negative and very close to zero. So definitely not 3. So from our perspective, if the result 3 is correct, black holes that were observed are actually horizonless objects. But of course, like all results in quantum foundations, you have a set of assumptions, you get the conclusion that you don't like, and then you have to choose your poison. So I'm not pushing it beyond that statement. So it's really if and then statement, which we can write very neatly. If these observations are correct, then astrophysical black holes are not physical black holes. Now, more conventionally, and that's what we are working on now, so I think I can say, sort of skip most of it, quasi-normal modes and light rings. That's how people try to distinguish between, say, Kerr-Schwarzschild black holes and black hole mimickers, because in long time, so close to the late time ring down and tails, there will be differences. There are possibly also slight difference in the light ring and shape of the light sphere as visible. Yes, we started to play with it. With physical black holes, we get slightly different boundary conditions simply because effective coordinate goes to finite radius, maybe slightly different shape. How much? We don't know yet. We tried the low-hanging fruit static k=1 solutions, because what we know near horizon geometry, we don't know full solution. So we use Padé approximations. It's one of very neat ways of combining far and near data, and just tested them on known models to see how well it works with some other useful methods. And it works. It gives interesting results. We found something that people conventionally overlook, and that holes and limitations of this approximation, calculated light rings, and now we're going to do it for dynamical case, so at least for frozen dynamical case, and that's what's going to be interesting. So to summarize, okay, if black holes exist, they require as exotic matter as wormholes. Sorry, almost as exotic as wormholes, and definitely as exotic compact objects, or maybe even more. So the first cheap argument against exotic compact objects, because they're impossible, because they're exotic, fails, because black holes are also exotic. Of course, we can still stick to the class 1 asymptotic solutions. Also, no paradoxes there. Some of the popular models of regular black holes are wrong. Spherical black hole formed in finite time within semi-classical physics cannot grow. So those stages are wrong. If spherical black hole is formed, it stops growing. We get finite redshift, finite collapse time, but we don't know if we do have physical mechanism which can provide enough negative energy density to accommodate it. So that's a big if. And until this is resolved, we cannot honestly start saying there is information loss paradox, simply because we don't know if there is a horizon. So there are interesting observations for cosmology, quantum normal modes, light rings. Again, maybe, so for cosmology, yes, we had this result. But whether it's visible in quasi-normal modes and light rings, maybe yes, maybe no. Geometry is different, properties are different, but the important question is whether observable properties are different. And of course, I have to thank my collaborators, Rob Mann and Valentina Bacchetti, with whom we started all this. My former student, Sebastian Merck, who is now in transition between Okinawa and Prague. Yanis Saranidis, who is on the way to Fudan Phil Simovich, who was Rob's student, my postdoc, and now faculty in University of Waterloo, Sam Harana, Pravin Dahal, who is now at CSRO, and yeah, advertising. Because Phil is now faculty, which is good. I don't have a postdoc, which is bad. So if you have somebody in mind to work on one of the questions that I saw, right, describe, and it's only 12 months because I cannot promise anything else. I don't know what's going on. Please contact me. I'm looking. And thank you very much. Hey, yeah.
Most black holes out there, if you just take a very conventional picture of black hole formation from stellar collapse and from, aggregation, galaxy centers, they should be very close to extremal Kerr solutions.
No, not too extreme. At least 30% of it has very low angular momentum, according to plus data. There will be some extreme ones, but again, they shed off angular momentum, and usually very rarely we get really high angular momentum things. But again, I don't. What I know, unfortunately, not much about rotating black holes, is that all the most natural generalization, curve idea solutions. So they all violate null energy condition.
Right. Yeah.
And what we showed again, and you can get, and for curve idea, you can get growing black hole, shrinking black hole, growing white hole, and shrinking white hole. What we showed that, well, I think shrinking white holes, you get some interesting singularities, which probably make them unphysical even with very relaxed conditions like mine. But if your main point is that, okay, spherical is nice, say something about rotating, we're trying to.
Well, I was just wondering if this paradox observational paradox that you gave, does that still hold if the black holes that you're talking about?
I thought so, but in their model, they took them spherical. So within the data, so I agree with you, but I'm sticking to their paradigm of the data analysis.
I mean, no rotating.
Yeah.
Questions?
Yes.
So for these other compact objects.
Yeah.
Or horizon, this kind of, I mean, is there a formation mechanism for any of those things? The standard one for stellar collapse, it's hard to see how you get anything else besides a thing with the horizon.
As far as I know, actually, almost no. For example, because almost all those models are given as static solutions that already exist. I think in the review of Cardozo and Pani, they have like a spread list of all those models, and they have a call on the formation mechanism, and I think almost on all of them there is X that is unknown. What I haven't talked about is that one of the objects on those exotic mimickers are wormholes. And for them, there was no formation mechanism. I tried to see if our mechanism generates, one class generates one class of wormholes, another class generates another class of wormholes. What happens is, while the static solutions to which we want to reach as a limit are perfectly fine, the dynamical one lead to violation of quantum energy inequalities, and therefore, dynamically, wormholes cannot be formed within, let's say, validity of semi-classical physics. That was the point where my kids stopped talking to me, because it sort of rules out Star Trek wormholes, but allows still, it doesn't forbid formation of wormholes from, at the first 10 to the minus whatever seconds of the universe, where it's strong quantum gravitational effects. So Honor-Harrington universe is safe where it's precious resource. Yeah. So one of the ways of our approach, because it works with trapped surfaces, it cannot pick out any of other mimickers, but it looks like, at least again in spherical symmetry, popular wormhole solutions cannot be reached dynamically, and those solutions that can be reached dynamically will kill you.
So we thank time again, and then we convene at 2.